Let's go ahead and find the work done in pumping the water out of this trough. So we're going to pump it right out the top, just over the edge. The acronym we use to find work is the integral of ADD volume. And the volume here that we're referring to is the volume of a slice. So the volume of a slice here is a long, thin, rectangular slice of water. Let's go ahead and start putting in our substitutions. So we will be integrating 0 to 7. So there are slices of water between 0 and 7 meters, since the trough is 7 meters tall. And then A is acceleration due to gravity. And then density, we are dealing with water, so the density of water is 1,000 kilograms per meter cubed. And then the second D right there, that is the depth. And by depth, we mean the depth of our representative cross-section. So we think of this as the cross-section at a height of y. Its depth, or its distance traveled, is going to be 7 minus y. So if we draw the front of the trough like this, and we're taking our representative cross-section right there, since this full distance is 7, this partial distance, the distance traveled by that cross-section, is 7 minus y. Okay, and then we have to figure out the volume. And by volume, again, we mean the volume of a slice. So the volume of a slice is going to be the width of the slice of water multiplied by the length of the slice of water, which is 10, multiplied by the thickness of the slice of water, which is dy. So the hard part here is going to be finding this width right there. So that width is going to go here, and then we multiply by 10, and then we multiply by dy. So all of this right here is the volume of the slice. Now, in order to figure out that width, we are going to imagine a coordinate system right here. And the 2 points on this line are going to be 7 halves, comma 7. We know that this piece right in here is 3.5, so that's 7 halves. And it's 7 all the way across. So this little piece that's going to come down here is going to be 7/4. And so this point right here is going to be 7/4, comma 0, because 7/4 plus 7/4 is going to be 7 halves. So both the distances right here and right here are the same, right? Those are both 7/4. So once we have the coordinates of the points on that line, we can now use the point slope formula to figure out the equation of that line. So I will have y minus 0 equals the slope, and the point, I'm using this as my reference point, so it's y minus 0 equals the slope times x minus 7/4. The slope is the change in y over the change in x in moving between these 2 points. So we will do 7 minus 0. Let's do the slope up here. So the slope is y minus y, 7 minus 0 over 7 halves minus 7/4. Well, 7 halves minus 7 fourths is 7 fourths. So we have 7 divided by 7 fourths, multiply by the reciprocal, and we will get 4 as the slope. So this will be a 4 coefficient right there. So the trough will have this, the edge of the trough will have this equation. Now, that width is a horizontal distance, so we need to isolate x. We need the equation of this line to be rewritten in a way that it is generating horizontal distances. Now, since I've isolated x, that is now measuring a horizontal distance. Now, it's not all of w though, right? This is just measuring from the y-axis over. So it's measuring exactly half the width of that element. So therefore, w will be 2 times x, which will give us 1/2 times y plus 7 halves. So there we finally have the width of the representative element for this trough. Let's start plugging things in. So out front we can pull out the 9800, and then we can pull out the 10, so we're going to get 98,000 in front. Integral 0 to 7. We will have 7 minus y. And we've pulled out the 10, so all we have left here is the w. I'm going to pull out the denominator of 2 and write this as y plus 7. So there's the width. The width is y plus 7 divided by 2. That's pop into the front with the 2. Then we just need to rewrite this, so we can rewrite this as 49,000. And inside, if we put this in descending order, we'll have negative y squared. And then notice that when we do the foiling, negative y times 7 is negative 7y, and positive 7 times y is positive 7y, so we have that part's canceling. And then we have plus 49. All right, so we will have 49,000 out in front. And then we will do our integration. We will get negative y cubed over 3 plus 49 times y. And that's from 0 to 7. So we will have 49,000 multiplied by, when we plug in 0, we won't get any volume there, or any work, I guess. We're finding work, so we'll get no work there. Plugging in the 7 is going to give us negative, let's see, 7 cubed is 7 times 7, which is 49, times 7 is 343. So we'll have negative 343 divided by 3. And then when we plug in 7 there, we have 49 times 7, which again is 7 cubed, which is 343. We can factor the 343 to the front. So I'm going to think of this as 49,000 multiplied by 343 multiplied by negative 1/3 plus 1. Negative 1/3 plus 1 is 2/3. So then we will cancel and combine, do whatever we can. Actually, we're going to end up with a denominator of 3 because the numerator is not going to be divisible by 3. And if we multiply this all out, we are going to end up with this fraction. And we are talking about work. Work is a Newton meter or a joule. So here is the amount of work done in emptying this trough out the top. let me say one thing about this. Sometimes you will find these vessels and they'll ask you to empty it out a pipe that goes above the object or something. So maybe we have a drain pipe over here and we're going to pump it out from a drain pipe that's a little bit taller. Let's just suppose that this was 2 meters tall. So instead of pumping it right out the top, we're going to pump it out this pipe that extends 2 meters above the trough. Well, the only thing that changes is this quantity right here, the distance traveled by a cross-section of water. We still have water between 0 and 7, so our limits of integration don't change. We still are moving those cross sections from 0 to 7 out. The only difference is the distance they travel would be 9 minus y if the exit point were 2 meters above.